In this video, we discuss distributed hash tables, or DHTs for short. A distributed hash table is essentially a hypercubic overlay network. We assume that you are familiar with the concepts of overlay networks and hypercubic networks. A distributed hash table can be used to store data reliably. The DHT is resistant to churn, so the machines which make up the system will leave and join the system at high rates. No machine in the system can see the whole picture, but the entire system is nevertheless highly reliable. To construct our DHT, we start out with a hypercubic network. For simplicity, we just use a standard hypercube. This is a hypercube in 2 dimensions with only 4 nodes. In reality, the hypercube will maybe have 20 or more dimensions, with millions of nodes. But 2 dimensions is about the maximum we can easily fit on a screen. Each node has an ID, so with 2 dimensions, each node has an ID with 2 bits. With 20 dimensions, each node has an ID which is a bit string with 20 bits. Each node has 2 zones, a core and the periphery. Now let's populate our hypercube with machines. The machines can be core machines, or periphery machines, like this. The idea is that core machines pretty much stay where they are, whereas peripheral machines can easily move around between different nodes. Periphery nodes can also move into a core, but when a peripheral machine becomes a core machine, it doesn't move anymore. The general idea is that every node has about the same number of machines. We assume that our DHT system experiences high churn, that is, machines join and leave the system at high rates. If a machine joins our system, it will just join an arbitrary periphery using some bootstrap mechanism, like this. Machines can also crash. If a peripheral machine is crashing, it's no big deal. The more problematic case is a core machine crashing, and it's even worse if that core already only has a small number of core machines, like in the node 11 here. If a node only has a few core machines left, peripheral machines must come to the rescue, and they go into the core to help. If a peripheral machine moves to the core, it quickly learns all the information from the other machines in that core. All machines in a core always try to have exactly the same data. Now node 11 is without a peripheral node, that can be fixed by having another peripheral node move to the periphery of node 11. You might start to wonder how this hypercubic network is used to store data. The idea is that the information about any file is stored with every core machine of one node. More precisely, take the ID of some data, for instance a movie name. We hash the ID with a commonly known standard hash function to a bit string, and then we take the first bits of that bit string. In our case, we only have a 2-dimensional hypercube, so we only take the first 2 bits, which is 11, and we store the information about the data with the machines in the core of node 11. This doesn't mean that these machines have to store the movie themselves. They could also just simply know how to find the movie, for instance know which machines actually store the movie. If the location information changes, these core nodes 11 update their forwarding information. We haven't discussed how to apply the overlay network. The hypercube nodes are just an abstract concept, so we have to discuss how the machines actually connect with each other in the overlay. This is a good point for you to quickly pause the video and think about this question for yourself first. Let's discuss this from the point of view of this machine here. First, the machine needs to be connected to all machines in the same node. These connections make sure that our machine knows what's going on in its node. Then it also needs to connect to machines in neighboring hypercube nodes. It could be connected to all of those neighboring machines, or to just some of them. Now it looks like our machine is connected to many nodes. However, if we have a 20-dimensional hypercube, the machine is only connected to a logarithmic number of machines in the same node, and a logarithmic number of machines in the neighboring nodes. In other words, even with 20 dimensions and millions of nodes, each machine would only be connected to roughly 20 machines in the same node and maybe just 20 hypercube neighbor machines, so in total to 40 machines. This is quite manageable for an overlay network. If a neighbor node machine is crashing, our machine can simply ask its peers in the same hypercube node whether they have another contact in that neighboring hypercube node, and then ask that contact for a new neighbor in that node. What if an adversary is constantly attacking the machines in a particular hypercube node? As usual, there are limitations regarding the fault tolerance of a distributed system. If an attacker manages to take out all the machines in the core of a particular Hypercube node before the peripheral nodes can come to the rescue, we are in trouble. So it's really a race between an adversary, trying to crash some particular set of machines, and our periphery nodes working as firefighters, moving to the right location quickly enough. Is there a smart way to learn which nodes are underpopulated and need help? Yes, absolutely. If a node is in trouble, the machines of that node will send rescue messages to their neighbor nodes, which then send periphery machines for help. The machines can also do some global accounting. Because a machine is neighbors with all machines in its Hypercube node, each machine knows how many machines there are in its Hypercube node. Then any machine can talk to its neighbor in the first dimension, with the first bit being different, and learn how many machines that node has, and as such compute how many machines in total there are in the nodes whose ID ends with a 1, in this case there are a total of 7 machines. The nodes ending with 0 do the same and learn that they are 9 machines. Now if our machine talks to its neighbor with the second bit being different, it can learn about the number of nodes in total, in this case 7 plus 9 being 16. This way every machine learns that one peripheral machine should move from a node ending in 0 to a node ending in 1 so that the whole system is more balanced. This may not be very impressive with only 2 dimensions, but with 20 dimensions it's a nice way to get a summary of what is going on in only 20 rounds of parallel communication. If a big attack is going on, and much fewer machines are joining than leaving, we risk that it is not sustainable anymore to run a high-dimensional Hypercube. If the total number of machines falls below a given threshold, the nodes remove a dimension of their Hypercube. In other words, the nodes with the same ID but only the last bit being different may merge, like this. The machines merging must learn from each other because after merging they will be responsible for twice the amount of data. Likewise, if there is too much redundancy in the system, the Hypercube can also add a dimension by splitting each node into 2, adding either a 0 or a 1 bit to every node. This completes our video. We have shown how to build a fault-tolerant and efficient distributed hash table. Dozens of designs for distributed hash tables exist, each based on a different hypercubic architecture with advantages and disadvantages. But fundamentally, they all work the same way as we have seen in this video. Thanks for watching this video.